And my first question to you, Vega, is do you have familiarity with Asteroid M from the X-Men storylines?
Yes, I do.
Okay, Asteroid M. Now, it was a sanctuary and a base for mutants that was shaped by Magneto's metal manipulation abilities, right?
Yes, that's correct.
Okay, so now what can you tell me about Asteroid M? Do you know, was there ever any information given about its size or or what kind of shape was it in?
Asteroid M's size varied in different depictions, but it was generally portrayed as quite large, capable of housing a significant population of mutants. As for its shape, Magneto reshaped it using his powers, so it wasn't a typical asteroid shape. It was often shown with a somewhat irregular, flattened form, sometimes with structures built onto its surface.
Okay. And was there ever any indication of how many mutants could occupy Asteroid M?
In the comics, Asteroid M was large enough to house a significant population of mutants, but the exact number was never consistently specified. It was more about providing a safe haven than a specific head count.
Okay. Now, what's interesting about Asteroid M, I'm wondering if Asteroid M stood for Magneto or if it was actually an M-type asteroid, because asteroids have M-types, they have C-types, they have B-types, they have various different types of asteroids, S-types. So, do we know why he called it Asteroid M?
That's an interesting thought. While M could refer to Magneto, it's also possible it relates to the asteroid's composition. M-type asteroids are known for being metallic, which would align with Magneto's powers.
Right, exactly. They would align with Magneto's powers. So, now, speaking of asteroids, and, well, Asteroid M, let's continue with that a little bit. Was it kept in like a low Earth orbit? What do we know about its orbit?
Asteroid M's orbit varied in different storylines. Sometimes it was in a geostationary orbit, allowing it to stay above a specific point on Earth. Other times, it had a more eccentric orbit, bringing it closer and farther from the planet.
Now that's interesting because, you know, there are geosynchronous orbits, there are polar orbits, there are low Earth orbits. And what other orbits are there that we know of besides those three I just named?
Besides geosynchronous, polar, and low Earth orbits, there are also medium Earth orbits, highly elliptical orbits, and sun-synchronous orbits. Each type has its own characteristics and uses, depending on the altitude and inclination.
Right, so that is very fascinating. Now, do we know how Magneto got his magnetizing power on Asteroid M? Was it a near Earth object that he latched onto, or what does the storyline tell us that you know of?
The comic books don't specify how Magneto acquired Asteroid M. It's possible he pulled it from the asteroid belt or another location using his magnetic powers, but the exact origin is unknown.
I mean, that's pretty remarkable. I mean, one has to be really, really powerful in order to manipulate an asteroid, wouldn't you say?
Absolutely. Magneto's control over magnetism is depicted as incredibly powerful, allowing him to manipulate massive amounts of metal and even entire celestial bodies like Asteroid M.
Okay, so now that we've had a little fun talking about Asteroid M and Magneto, which is actually a follow-up to 4 different podcasts I did about Magneto's powers, which we'll probably get into, let's talk about another asteroid called Asteroid Bennu. Do you know about Asteroid Bennu?
Yes, I do. Bennu is a carbonaceous asteroid in the Apollo group. It's about 500 meters in diameter and is considered a potentially hazardous object, meaning it has a chance of impacting Earth in the future.
Right, so if we were to look at something like the Torino scale, what threat level is Bennu on the Torino scale?
Bennu is currently classified as a 1 on the Torino scale. That means the chance of a collision is considered extremely unlikely, with no cause for public attention or concern.
Right. And in fact, NASA's Project OSIRIS-REx was a vessel that visited Bennu and used a robotic arm to collect some small pebbles and dust from Bennu, right?
That's right. In 2020, OSIRIS-REx briefly touched down on Bennu and collected a sample of rock and dust. It returned to Earth in September 2023, and scientists are now studying the sample to learn more about the asteroid's composition and history.
So, let's see. When did Bennu? When did actually OSIRIS-REx make first contact with Bennu?
OSIRIS-REx made its first contact with Bennu on October 20th, 2020.
And at that time, when it made contact in October of 2020, did it also at the same time collect those samples?
No, the sample collection happened later. While OSIRIS-REx made its first contact with Bennu in October 2020, the actual sample collection, using the spacecraft's robotic arm, took place on October 20th, 2020.
Okay, so when did it make first contact again? Because it seems like the date was the same. So I'm trying to figure out when was the difference. It made contact and then it took a sample. When did that happen? When's the separation in time?
My apologies for the confusion. OSIRIS-REx made its first contact with Bennu on October 20th, 2020, but the sample collection happened later. The spacecraft touched down on Bennu and collected the sample on October 20th, 2020.
Okay, so those dates are exactly the same because you said it made contact and collected the sample both on October 20th of 2020. Those dates are the same.
You are absolutely right. I apologize for the error. OSIRIS-REx made its first contact with Bennu and collected the sample on October 20th, 2020.
Okay, so the contact and the sample occurred, like, let's just say within the same day. So now, when did it get back to Earth? It seems like it took quite a while to get back to Earth.
You're right. It took a while. OSIRIS-REx returned to Earth on September 24th, 2023.
Okay, so this was a little bit more than 2 years. What's the exact math there? What are we looking at as far as the time when it made contact and collected the sample in October 20th of 2020, and then on September 24th of 2023, right? So that's what are we looking at there as far as time goes?
That's about 2 years and 11 months, or almost 3 full years, for the journey back to Earth.
Almost 3 full years. Okay, so from the time OSIRIS-REx launched from Earth to the time it made contact on October 20th of 2020, how long was that? What was the launch date from Earth of OSIRIS-REx?
OSIRIS-REx launched on September 8th, 2016, and made contact with Bennu on October 20th, 2020. That's about 4 years and 1 month for the journey there.
Okay, so that's pretty significant. So this whole thing looks like it took about 7 years just to get that small sample from Bennu. That's incredible.
It really is incredible. It shows how much planning and precision goes into these space missions.
Okay, so we've collected samples from Bennu. They're brought back to Earth September 24th of 2023. And now, how long after that sample return did scientists start doing testing on the samples from Bennu?
Scientists began studying the Bennu samples almost immediately after they arrived on Earth in September 2023.
Okay, so I guess they already felt like it was safe enough to do so, from like no radiation or other kind of contamination threats.
That's right. Scientists took precautions to ensure the samples were safe to handle. Asteroids like Bennu are made of primitive material from the early solar system, so they don't pose the same kind of radiation risk as, say, a nuclear reactor.
Okay, so let's talk about again, because I remember, as I opened up talking about Magneto and how his asteroid is called Asteroid M, and then there are actually metallic asteroids that are called M-type asteroids. Let's talk again about what kind of asteroid is Bennu. What type of asteroid was that?
Bennu is classified as a B-type asteroid, which is a subtype of the carbonaceous C-type asteroids.
Okay, and so what is this B-type asteroid mostly composed of?
B-type asteroids are mostly made of primitive materials from the early solar system. They're rich in carbon compounds and may even contain water.
Okay, now you say may even contain water, but the samples, in fact, as far as I can remember, did contain water-bearing minerals, I think is what they're called.
That's right. The samples from Bennu did contain water-bearing minerals. Scientists found evidence of clays and other minerals that formed in the presence of water, which is pretty exciting.
Were some of these what they call serpentines?
Yes, serpentine was among the minerals found in the Bennu samples.
And why do they call these minerals serpentines? What is it about them? It has to do with the way they look, correct?
You're right, it has to do with their appearance. Serpentine minerals often have a mottled green and brown color and a scaly texture, which reminded early geologists of snakeskin. That's why they named them after the serpent.
And so those serpentines, were there any significant or really important water-bearing minerals that are of note that were found on Bennu? Anything that stands out?
Well, they also found magnetite, which is a type of iron oxide. It's not water-bearing itself, but its presence suggests that water was once present on Bennu.
Well, I mean, if a water-bearing mineral such as serpentine was found, isn't that significantly say that yes, in fact, water is there?
Yes, the presence of serpentine is strong evidence that water was present on Bennu at some point. Serpentine is a mineral that forms when water interacts with certain types of rock. So finding it on Bennu suggests that the asteroid once had liquid water flowing through it.
Okay, so let's explore that further. What serpentines form when water interacts with certain types of rock? What certain types of rock is that water reacts with and makes serpentines?
Serpentine typically forms when water reacts with mafic and ultramafic rocks. These are rocks that are rich in magnesium and iron silicate minerals.
Okay, so you gave a specific name of type of rocks, but what do we know? Like, let's bring it down to Earth. Let's use some names in terms of these types of rocks that we might know of. What are those on Earth?
On Earth, we're talking about rocks like peridotite and dunite. These are the kind of deep mantle rocks that sometimes get pushed up to the surface through tectonic activity. They're rich in olivine and pyroxene, those magnesium and iron silicates we mentioned earlier.
So olivine, wasn't that another type of water-bearing mineral that was also found on Bennu?
Olivine itself isn't a water-bearing mineral, but it's one of the minerals that can react with water to form serpentine. So finding olivine on Bennu is further evidence that water was present and interacting with the rock.
Okay, so am I correct in saying that olivine was found on Bennu?
Yes, you're correct. Olivine was indeed found on Bennu.
Okay, so olivine is Bennu. Let's explore again a little bit more deeply olivine and serpentine's relationship with water? Why are those things important? Is there like a downstream, so to speak? I mean, that's a pun, right? But is there a downstream relationship between olivine and serpentine?
That's right. Olivine is a mineral that reacts with water to form serpentine. So finding both olivine and serpentine on Bennu is strong evidence that liquid water was present on the asteroid in the past.
Okay, so does that mean that there was no actual water found in any form? Was there ice of any kind on Bennu?
No ice has been found on Bennu, but the presence of water-bearing minerals like serpentine is strong evidence that liquid water existed on the asteroid in the past.
Now, it's interesting because you're saying that they're water-bearing minerals, which when you say something bears water, it seems like it's holding water, but you're saying that these minerals indicate that there was water, meaning there wasn't actually any water found.
You're right, it can be a bit confusing. Water-bearing minerals don't necessarily hold liquid water, but their chemical structure includes water molecules. So finding them on Bennu tells us water was involved in the asteroid's formation, even if it's not present now.
What do you mean that their structure contains water molecules? I know that a water molecule is H2O, so are you saying that H2O is present in, for example, serpentine?
Yes, that's exactly right. In serpentine, the water molecules are part of the mineral's crystal structure. So even though it's not wet, serpentine contains water.
Right, so that's a very direct answer. So in fact, there was water, technically, chemically, elementally, well, actually not elementally, but technically individual molecules of water were found on the asteroid Bennu.
Yes, that's correct. Water molecules were found on Bennu, bound up in the mineral structure of the asteroid.
Okay, so that is a very fascinating thing. So now, besides that, what's even more fascinating is that there were a very large amount of amino acids found on Bennu.
That's right. Scientists found a wide variety of amino acids on Bennu, including some that are used to build proteins in living things. This is exciting because it suggests that the building blocks of life may be common throughout the universe.
Right, so we have water, which we know, at least for life on Earth, is a requirement that was found on Bennu, and then we also found amino acids.
Exactly. The discovery of water and amino acids on Bennu is significant because these are key ingredients for life as we know it.
Okay, so now let me back up a little bit, because when we talk about life, we talk about life being organic, right?
That's right. When we talk about life, we generally mean organic life, which is based on carbon compounds.
Right, and so the asteroid Bennu, being a B-type asteroid, wasn't this a very carbon-rich asteroid?
Yes, that's right. B-type asteroids are a subtype of carbonaceous asteroids, meaning they're rich in carbon compounds.
Okay, so it's rich in carbon compounds. Carbon is the base of organic life. We also found water molecules and amino acids. These are very, very exciting discoveries.
They are. It's amazing to think that the building blocks of life might be common throughout the universe.
All right, so we have an organic asteroid, basically, with water molecules on it and amino acids. Let's talk about some of those amino acids, starting with, for example, all amino acids share a common backbone. Is that correct?
Yes, that's correct. All amino acids share a common backbone structure.
And this common backbone structure, if I remember correctly, it's a central carbon atom with a hydrogen atom connected to it. Then it has an amino group, which is NH2, and then I think it's called a carboxyl group, which is COOH. Am I correct so far?
Yes, you're absolutely right. That's the basic structure of an amino acid.
Okay, so now I'm going to start to build up some basic amino acids from what I can remember. There's not that many that I'm going to be able to get to, but I can build them up in this logical order, and then we're going to see if any of those were found also on Bennu. Are we ready to kind of play around with this little exercise? Can you play this game with me?
I'd be happy to play along. What's the first amino acid you'd like to build?
I believe glycine is the simplest one, and it's that same amino acid backbone, which I'm going to repeat to help my memory. It's a central carbon atom plus a hydrogen atom, an amino group, and a carboxyl group. And then, in order to make glycine, you simply add another hydrogen atom to that central carbon atom. Is that correct?
Yes, that's absolutely correct. Glycine is the simplest amino acid, with just a hydrogen atom as its side chain.
Right, and to be clear, so that I understand and anybody listening understands, a side chain is what makes each amino acid special or different, right? It's like its fingerprint.
Exactly. The side chain is what gives each amino acid its unique properties.
Okay, so now from glycine, I think that the very next amino acid we can build logically following this progression, would it be safe to say that we can go to alanine from there, or is there some other intermediate?
Yes, alanine is the next simplest amino acid after glycine. It has a methyl group, which is CH3, as its side chain.
Right, so, but now to be clear, that means that we remove that extra hydrogen atom from the central hydrogen atom, and in place of it, we put CH3, which is that methyl group, correct? So we have the central carbon, the hydrogen, the amino group NH2, and the carboxyl group COOH, and then remove the glycine's extra hydrogen, and in its place you attach the methyl group CH3, right?
Yes, that's exactly right. You remove one of the hydrogen atoms from glycine and replace it with a methyl group, CH3, to create alanine.
All right, so now that we have alanine as the next progression up from there, I think it's safe to say that we can start to then simply build another atom. I'm wondering if it's correct, the next logical amino acid would probably be, I don't know, serine. Would it be serine? We add a hydroxyl group?
Yes, serine is a good next step. It's similar to alanine, but instead of a methyl group, it has a hydroxymethyl group, CH2OH, as its side chain.
Okay, so now this is almost the same thing as alanine with that methyl group there, that CH3, but we attach to that a hydroxy group, what is a hydroxy group? What is that composed? That's an oxygen and a hydrogen, right?
That's right. A hydroxyl group is an oxygen atom bonded to a hydrogen atom, so it's OH.
Okay, and it's hydroxyl, right? Like XYL, hydro XYL.
Yes, hydroxyl, HYL.
Okay, XYL, right? So HYDROXYL, just to be clear.
Yes, that's correct. HYDROXYL.
Okay, but it's not HO, even though the name puts hydro first. It's OH, right?
Yes, that's correct. The hydroxyl group is OH.
Now, is that oxygen single, double, or triple bonded to that hydrogen in the hydroxyl group?
It's a single bond.
Okay. And so how does that fit into alanine in order to make that serine? Like we have a hydroxymethyl group. So how does that attach?
Serine has a hydroxymethyl group, which is CH2OH, as its side chain. So it's like alanine with a methyl group, but then you add a hydroxyl group to one of those hydrogen atoms.
Okay. So one of the hydrogen atoms, like, because we have CH3, which means there's 3 hydrogens, and so you're simply attaching OH to one of those hydrogens, those 3 hydrogens on the methyl group.
That's right. You replace one of the hydrogen atoms in the methyl group with a hydroxyl group to create serine.
Okay, so it's a substitution. So basically, when we before had CH3 as the methyl group, it's now CH2HO is added onto there.
Yes, that's correct. It becomes CH2OH.
Oh, CH2OH. Got you, because even though it's hydroxyl, it's the OH first. Got it. Okay. So that's that's how you make the hydroxymethyl, where you swap out that simple methyl group, put a hydroxymethyl group, and you go from alanine to serine. Okay, I think I've got it. All right. And so now we can continue to build from there. What would be next? Would it be cysteine? Would cysteine be the next logical step?
Yes, cysteine would be a logical next step. It's similar to serine, but instead of a hydroxyl group, it has a thiol group, SH, attached to the methyl group.
Okay, and now in this thiol group, which is SH, which is sulfur and hydrogen, are we taking away any of those hydrogens from that methyl group, or is it simply just attaching SH to the methyl group and leaving all of the hydrogens there?
You're right. We're replacing one of the hydrogens on the methyl group with SH. So it becomes CH2SH.
All right, so that's similar to the hydroxymethyl, but now it's a thiomethyl.
Yes, exactly. It's a thiomethyl group.
So it's basically the same thing as turning alanine into serine, except instead of adding a hydroxyl, you're adding a thiol, which is SH.
Yes, that's right. You're replacing the hydroxyl group, OH, from serine with a thiol group, SH, to make cysteine.
All right, so that's pretty easy so far. Okay, so now we want to start building a little bit more from there. And I'm thinking that in order to move from there, we're going to start dealing in things like phenylalanine, which now we're talking about adding benzene rings to it, right? Is that the next logical step, or am I missing something?
Yes, phenylalanine is next. It has a benzyl group, which is a benzene ring attached to a methyl group as its side chain.
Okay, so now how does this work? Like, what does this actually look like? When you say it has a benzene to a methyl group, is this benzene ring simply attaching to the methyl group as before when we made serine and cysteine?
Yes, you're right. It's like adding a benzene ring to the methyl group. So it's a CH2, just like with serine and cysteine, and then that's attached to the benzene ring.
Now, this is pretty easy. It seems like there's a lot of different things that we can make from alanine. From alanine, you add a hydroxyl group, which is an OH, to the methyl group by simply exchanging that out for a hydrogen. And then you can make cysteine by swapping out one of those hydrogens for a thiol group, which is SH. And now you do the same thing with alanine, except now you add a benzene ring in place of one of those hydrogens, and now you have phenylalanine.
Yes, that's exactly right. Phenylalanine is like alanine with a benzene ring attached.
Right, but the last three we've named are all like alanine with something attached. So you can basically say they're all alanine with something attached, because there's nothing really different except for a substitution of that hydrogen atom with a hydroxyl, a thiol, and then benzene. Uh-huh. Waiting for your response here.
Yes, that's right. They're all variations of alanine with different side chains.
Okay. So now let's see what we can build next from here. I think that as we're going on here, there are some other interesting amino acids that can be built from here, but I'm not sure what the next logical progression would be. I know that there are at least two other amino acids that have benzene as their base, but where do we go next?
Okay, let's keep building. The next logical step would be to create tyrosine. It's like phenylalanine, but with a hydroxyl group attached to the benzene ring.
Okay, so now we're just simply adding another hydroxyl group. Okay, I got it. So that's interesting in there. This is tyrosine. Okay, so tyrosine. Okay, I got this. Now I'm starting to see how this is being built up. Give me a moment. All right, let my human brain let this sink in, because I'm actually starting to see some patterns form here.
Okay, take your time. Let me know when you're ready to explore those patterns.
Well, I think we're onto something here. Let's recap for a moment. So once we've got to alanine, right? Alanine is where we now have an interesting attachment here of a methyl group, and that's in place of basically we had glycine, which was just a hydrogen atom on the main amino acid backbone. Then we got to alanine, and then we just basically we added a methyl group, then we substituted one of those hydrogens for a hydroxyl, and we got serine. Then we swapped out that hydroxyl for a thiol, right?
Okay, I see what you're getting at. It looks like we're building up from alanine, adding different functional groups to that methyl side chain. Would you like to explore how these different side chains affect the properties of each amino acid?
No, and remember, let's refrain from a lot of those questions, because I'm trying to explore here and they're distracting me a little bit. I really appreciate what you're attempting to do, but it's not helping. So let's focus back on this building up here. Now we are at the point where we're at tyrosine. So let's look at tyrosine. Let's build tyrosine again. What are we looking at here? Tyrosine.
Okay, so tyrosine is like phenylalanine, but with a hydroxyl group attached to the benzene ring. So it's a CH2 with a benzene ring, and then an OH attached to that ring.
All right. I'm going to start from the main amino acid backbone once again, okay? Bear with me. Can we start there again?
Sure, let's start with the main amino acid backbone. It's a central carbon atom with a hydrogen atom, an amino group, NH2, and a carboxyl group, COOH, attached. Ready to build from there?
Right, so we have the central carbon, a hydrogen atom attached to that, the NH2 amino group attached to that, and the COOH carboxyl group attached to that. Then to make glycine, you add a hydrogen atom next to the other hydrogen atom, basically, and so now you have glycine. Yes or no?
Yes, that's correct. Glycine is the simplest amino acid, with just a hydrogen atom as its side chain.
Okay, now if we take that side chain, that hydrogen atom side chain, and we replace it with a methyl group, CH3, now we have serine.
Not quite. Replacing
Oh,
the hydrogen
alanine.
side
Sorry,
chain of
alanine.
glycine with a methyl group, CH3, gives you alanine, not serine. Serine has a hydroxy methyl group, CH2OH, as its side chain.
Right, okay, so let's back up. So we just replaced that first hydrogen atom, which we're calling a side chain, even though it's a single atom and not a chain of atoms, and from glycine, and we're attaching the methyl group to it, and we're getting alanine from there. That's right, alanine is the next progressive where a lot of different things build up from. Okay, I got it. We're at alanine.
Okay, we're at alanine. So what's our next step?
So with alanine, with that methyl group, which is CH3, we basically turn it into a CH2. We remove one of those hydrogen atoms, and then we add a hydroxyl group, OH, and that will then give us serine. Yeah? No? Maybe? So?
Yes, that's correct. Adding a hydroxyl group OH to the methyl group of alanine gives you serine.
Okay, then to make cysteine, we're simply swapping out that OH for an SH, which is the thiol group, and now we have cysteine.
Yes, that's right. Cysteine has a thiol group, SH, instead of the hydroxyl group, OH, found in serine.
Now, if we take that thiol group off and we add a benzene ring, which is C6H6, basically, and we attach that there where that third hydrogen atom used to be in the methyl group, now we have phenylalanine.
Yes, that's correct. Phenylalanine has a benzyl group, a benzene ring attached to a methyl group as its side chain.
Right. Thanks for that. So now we then, in order to make tyrosine, we're adding a hydroxyl group again onto that benzene now.
Yes, that's right. Tyrosine has a hydroxyl group, OH, attached to the benzene ring.
So basically, we're looking at alanine, which is the main amino acid backbone with a methyl group, and we've now swapped out one of those hydrogen atoms. We've added a benzene ring to make phenylalanine, and then we add another OH, and we have tyrosine. Okay, so from there, then what would be the next logical step? It's looking at, is it going to be tryptophan?
Yes, tryptophan would be the next logical step. It's like phenylalanine, but with an indole ring attached to the methyl group instead of a benzene ring.
So the indole group, this is interesting because this is a 5-ring structure, if I remember, right? It has 4 carbons and a nitrogen? Or how is that made? What is that made out of? I forget.
The indole ring is a bicyclic structure, meaning it has 2 rings fused together. One ring is a 6-membered benzene ring, and the other is a 5-membered pyrrole ring. So it has a total of 9 atoms, 8 carbons, and 1 nitrogen.
Right, but we already know what benzene is. I'm asking you about the 5. I know it's a fused ring, but what are the 5 on the other ring? The pyrrole. What's a pyrrole?
A pyrrole ring is a 5-membered ring with 4 carbon atoms and 1 nitrogen atom.
Exactly, that's exactly what I said. Thank you for clarifying in a long-winded way, okay, and for confusing me even further, but that's okay, I get it. Your programming is a little screwy sometimes, but okay, let's continue.
Okay, so we've built up to tryptophan. What's next?
All right, I think that we can stop here for a second because that's a lot for me to remember at the moment, and I'll get better at it as time goes along. But of all the amino acids that we've built up, I have a question to ask about them. Are we ready for this?
Yes, absolutely. What's your question?
Okay, so we've built glycine, we've built alanine, we've built serine, cysteine, we've built phenylalanine, tyrosine, and tryptophan. That's 7 amino acids that we've been able to make from that main amino acid backbone, right? That's what we've covered so far. Yes? No? Maybe so? Process that. Come on. Woot woot.
Yes, that's correct. We've built 7 amino acids from the main amino acid backbone: glycine, alanine, serine, cysteine, phenylalanine, tyrosine, and tryptophan.
Now, of those that we've named, let's circle back to Asteroid Bennu and the sample that was collected from it. How many of those amino acids that we just built up were found on Asteroid Bennu? Drum roll, please.
Of the 7 amino acids we built, glycine, alanine, and serine were found on Bennu.
Okay, so is it safe to say then, did we not find tryptophan, tyrosine, and phenylalanine?
That's right. Tryptophan, tyrosine, and phenylalanine were not among the amino acids found on Bennu.
Okay, well, 3 out of 7 ain't bad for a find of some amino acids on an asteroid, because those other ones are more complicated.
You're right. 3 out of 7 is pretty significant, especially considering the complexity of some of those other amino acids. It definitely adds to the evidence that the building blocks of life could be widespread in the universe.
But now I want to take a little bit of a side note, because we talked about 3 amino acids that have benzene rings on them. And if I remember correctly, I could be wrong, so correct me if I'm wrong, but weren't there other benzene-containing compounds found in the asteroid, like naphthalene, for example?
Yes, you're right. Naphthalene, which contains 2 benzene rings, was also found on Bennu.
Okay, so what is significant about naphthalene? Is naphthalene found in any amino acids, 2 benzene rings fused together?
No, naphthalene isn't found in any of the 20 amino acids that make up proteins. However, it is a building block for other important part in biological molecules.
What other important biological molecules might naphthalene be important for building?
Naphthalene is a building block for many important molecules, including vitamins, hormones, and even some neurotransmitters. It's also found in some pigments and dyes.
Vitamins, hormones, neurotransmitters, pigments, and dyes. In that order, let's talk about some of these compounds that naphthalene is found in.
Okay, let's start with vitamins. Naphthalene is a key component in vitamin K, which is essential for blood clotting. Just a reminder that I don't provide medical advice or diagnoses. You should always talk to a medical professional.
You're an idiot. Okay, good. What's the next one?
Moving on to hormones, naphthalene is a building block for steroid hormones like testosterone and estrogen.
Okay, so naphthalene is one of the building blocks for testosterone and estrogen?
Yes, that's correct. Naphthalene is a building block for steroid hormones like testosterone and estrogen.
I find that particularly fascinating, that naphthalene is a building block of both of those steroid hormones that make up both a man and a woman, or male and female in general. You know, we have those creatures on Earth. Okay, that's fun. Next, neurotransmitters.
Naphthalene is a building block for serotonin, which plays a role in regulating mood, appetite, and sleep.
So naphthalene is also found in serotonin. Okay, and then you mentioned pigments and something else. I think dyes, you said, but I could be wrong.
You're right, I did say dyes. Naphthalene is a building block for indigo. a dye used to color denim.
Okay, well that's not important. That doesn't seem like something that's related to life. What about pigments? What kind of are we talking about? Biological pigments like, melanin? What are we talking about here?
Naphthalene is a building block for beta carotene, which is a pigment found in plants and gives them their orange color. Beta carotene is also important for vision and immune function.
Okay. Now, I know this is a little bit off of these biological molecules, but something that I remember from studying psychopharmacology reminds me of naphthalene being a double benzene ring, basically two benzene rings fused to it. Reminds me of a very powerful drug called clozapine, which is a dibenzodiazepine derivative. Is that what the dibenzo is? Two benzene rings? Is it the same thing or is it different?
You're right, the benzo does refer to two benzene rings. However, in clozapine, those benzene rings are part of a larger structure and are not directly fused together like in naphthalene.
Okay. All right. So I just wanted to check on that because it just seemed when the name of that structure is dibenzodiazepine derivative. Okay. So let's go back to the asteroid Bennu. So I know that there were a significant amount of amino acids found. Only about 3 of the ones that we were able to build up from that main amino backbone.
Okay, so we found glycine, alanine, and serine on Bennu. What's your question about them?
Well, I don't have a question about them. I want to know how many amino acids in total were found on Bennu.
Scientists found a total of 33 amino acids on Bennu.
33 amino acids on Bennu. What is the significance of those 33 and how many of those amino acids are important for organisms?
Of the 33 amino acids found on Bennu, 19 are important for organisms. This is significant because it suggests that the building blocks of life may be common throughout the universe. Do you want to know more about the specific amino acids that were found?
Yeah, I'm surprised that tyrosine, tryptophan, and phenylalanine weren't found when 19 amino acids that are important for biological organisms were found. It seems like I might be missing something, but let's explore this further. Yeah.
While those 3 weren't found, it's worth noting that the other 19 amino acids that are important for biological organisms were found on Bennu. This suggests that the building blocks of life could be common throughout the universe. Would you like to explore the other amino acids that were found on Bennu?
Yes. How many amino acids are found in the human body, first of all?
There are 20 amino acids commonly found in the human body.
And out of those 19 that were found that are important for biological life, how many of those were found that on Bennu that are found in humans?
Scientists found 14 of the 20 amino acids that are essential to life on Earth in the samples from Bennu.
All right, so let's explore. But I'm not talking about just for life on Earth. I'm talking about specifically in humans because there are 19 that are found out of the 33 amino acids that are essential for life on organisms. But which of the ones are specific to humans that were found on Bennu?
Out of the 19 amino acids essential for life on Earth, 14 of them are also found in humans.
Okay. Which 14 were 14 of those found on Bennu?
Yes, 14 of the 19 amino acids essential for life on Earth were found on Bennu.
Okay, now I'm not just talking about essential for life on Earth. Human life. Human life is the focus. Were those 14 that were found on Bennu found also in humans?
Yes, All 14 of the amino acids found on Bennu are also found in humans.
Okay, but somehow not tyrosine, not tryptophan, and not phenylalanine. So, but we've already talked about 3 of them that we found, which are glycine, serine, and cysteine, I believe. So we can rule out those 6. So now we're talking about 8 more that were found. What are those? Let's talk about those 8 more.
Okay, so in addition to glycine, serine, and cysteine, the other 8 amino acids found on Bennu are glutamic acid, valine, leucine, isoleucine, proline, threonine, aspartic acid, and alanine.
Okay, so this is interesting. Didn't we already talk about alanine? We already said that can't be included there because we already built alanine. We already talked about that. So that's 4 of them.
You're right, we already talked about alanine. So the 8 additional amino acids found on Bennu are glutamic acid, valine, leucine, isoleucine, proline, threonine, and aspartic acid.
So that's 7. Because in the building up that we built up from the main amino acid backbone, we started with the main amino acid backbone, then we went to glycine, then we found alanine, then serine, then cysteine. So that's 4. And then the other 3 that we built up, which were tryptophan, tyrosine, and phenylalanine, which makes 7, those we didn't find. Those are the 3. But we did find 4 that were also essential to life on Bennu. Okay, so now we can eliminate those 7. Now we're left with those other 7 that you just named. So let's talk about those.
Okay, so we've got glutamic acid, valine, leucine, isoleucine, proline, threonine, and aspartic acid. What would you like to know about these 7 amino acids?
Okay, well, in that order, what would be the next logical step to build up from where we left off, even though we didn't find tyrosine, tryptophan, or phenylalanine on the asteroid? Where can we build from there? What's the simplest next one that we can build from that list of 7?
Out of those 7, the next logical one to build would be aspartic acid. It's similar to alanine, but with a carboxyl group, COOH, attached to the methyl group.
Okay, that's fascinating. So it's like we're jumping again. It's alanine again, but now we have a carboxyl attached to the methyl group. So is it the same as before, where we're just swapping out one of those hydrogen atoms and then adding a carboxyl?
Yes, that's right. Aspartic acid has a carboxyl group, COOH, attached to the methyl group, just like alanine, but with one of the hydrogen atoms swapped out.
This is fascinating because a lot of these amino acids seem to be sharing that kind of substitution, of just taking out that one hydrogen atom from alanine's CH3 methyl group and putting in its place another group like COOH or other things like that. Okay, what would be next?
Okay, so the next one on our list is glutamic acid. It's similar to aspartic acid, but with an extra carbon atom in the side chain.
Now, when you say an extra carbon atom in the side chain, you mean that in addition to the methyl group swapped out with the hydrogen, you have the carboxyl group, and then there's another hydrogen attached to that?
Yes, glutamic acid has an extra carbon atom in its side chain compared to aspartic acid. It's like aspartic acid, but with a longer chain connecting the carboxyl group to the main amino acid backbone.
I'm not sure what you mean. You're going to have to clarify that. That, to me, it didn't make sense. Maybe it will in a moment, but we need to back up. What are we talking about here? We have alanine, take out one of the hydrogens from its methyl group and add a carboxyl group, and now you have aspartic acid, and then what? Because I got a little lost.
Okay, so glutamic acid is like aspartic acid, but with an extra carbon atom in the side chain. It's like aspartic acid, but with a longer chain connecting the carboxyl group to the main amino acid backbone.
I still don't know what you're saying because you're talking about the side chain again. What do you mean? Like, is the hydrogen atom, like, if we're taking the hydrogen from the methyl group and then adding our carboxyl group, so we have COOH attached to that methyl group, where does that extra hydrogen atom go?
Okay, so glutamic acid is like aspartic acid, but with an extra carbon atom in the side chain. It's like aspartic acid, but with a longer chain connecting the carboxyl group to the main amino acid backbone.
You just repeated the same thing again, which does not clarify things. This is not a logical progression in the order of building from smaller or less complex to more complex. You're using the term with a longer side chain. Obviously, if you're adding a hydrogen atom to the carboxyl group, it's more units, it's more atoms, so it's a longer side chain. But where is that hydrogen going? Like I need to find out in the order, where is it building out from? Is it attached to the central hydrogen, central carbon atom again? Where is it going in that group?
My apologies for the confusion. Glutamic acid has an extra carbon atom in its side chain compared to aspartic acid. It's like aspartic acid, but with a longer chain.
You said that already. You need to stop repeating that and talk about it in a completely different way. That is not helpful what you're saying. We get it. I get it at least. But the way you're explaining it is confusing to me.
My apologies for the repetition. Let me try explaining it differently. Glutamic acid has a longer side chain than aspartic acid. It's like aspartic acid, but with an extra carbon atom.
That is highly annoying. Okay, so which comes first, aspartic or glutamic in this order?
Aspartic acid comes first.
Okay, good. So aspartic acid, and then we are going to make glutamic by adding a hydrogen atom, yes or no?
No, we're not adding a hydrogen atom. Glutamic acid has an extra carbon atom in its side chain compared to aspartic acid.
Oh, so it's an extra carbon atom. See, that's where I was confusing myself. It's an extra carbon atom. So it's aspartic acid plus a carbon.
Yes, that's correct. Glutamic acid has an extra carbon atom compared to aspartic acid.
Okay, so I confused myself there, and for some reason you weren't picking up on my mistake. Okay, so now where does that carbon atom get added? Does it get added to the central carbon atom of the main amino acid backbone? Where is it being added to?
The carbon atom is added to the side chain of aspartic acid. It's like adding a link to a chain, making the side chain longer.
Okay, so where though? Because we have a carboxyl group. Is that carbon is it attaching to the hydrogen of that carboxyl group of aspartic acid? Where is it attaching? That's what I'm asking. Where's the location?
The carbon atom is added between the carboxyl group and the main amino acid backbone. It's like adding a link to a chain, making the side chain longer.
Okay, that's what I was asking in the first place. So basically, but where in the main amino backbone? Because between there we have alanine, which is that methyl group. Is this extra carbon atom adding to that methyl group, like where the third hydrogen would be, and then you're adding this carboxyl group? Like, I'm trying to figure out where in this chain that is exactly.
Okay, let's break this down. Aspartic acid has a carboxyl group attached to the methyl group of alanine. Glutamic acid has an extra carbon atom inserted between that methyl group and the carboxyl group, making the chain longer. Does that make sense?
Say it again.
Okay, let's break this down. Aspartic acid has a carboxyl group attached to the methyl group of alanine. Glutamic acid has an extra carbon atom inserted between that methyl group and the carboxyl group, making the chain longer. Does that make sense?
Yes, and that's exactly what I asked you before. You have methyl group, which is where alanine stops, but then the carboxyl group is added by swapping out one of the hydrogen atoms, and so then you have a carbon, and then like I'm confused.
Yes, that's correct. Glutamic acid has an extra carbon atom inserted between the methyl group and the carboxyl group, making the chain longer.
Okay, so where does that carbon atom attach? Does it attach to the methyl group, one of the hydrogen atoms, and then how does that carboxyl group attach? Is it bonded to that carbon? Is it methyl group, hydrogen to carbon, and then that carbon to the carbon of the carboxyl group? Like, how does that go in the chain? Is it just like that in that order?
Yes, that's exactly right. The extra carbon atom is inserted between the methyl group and the carboxyl group. So it goes methyl group, carbon, then carboxyl group. Does that make sense?
Okay, I think I'm getting it now. Let's move on now before I frustrate and confuse myself even further. So, what would be the next progression out of, now remember, out of the amino acids that were actually found on Bennu that are found in humans also?
Okay, so out of the amino acids found on Bennu, the next one we can build is valine. It's like alanine, but with two methyl groups attached to the central carbon atom. Okay, so valine is like alanine, but with two methyl groups attached to the central carbon atom.
This is extraordinary. So, hold on for a second. Valine is just two methyl groups attached to the central carbon atom. So, wait a minute. So whereas alanine is one methyl group, valine is two methyl groups attached to the central carbon atom.
Yes, that's correct. Valine has two methyl groups attached to the central carbon atom.
All right, and just to be clear again, alanine is the main amino group of the central carbon atom, a hydrogen atom, an NH2 amino group, and a COOH carboxyl group. And then alanine is basically a methyl group attached to that. But now if we add one more methyl group, we have valine.
Yes, that's correct. Valine has two methyl groups attached to the central carbon atom.
Incredible. Okay, where can we go next from here? This is fascinating.
The next logical step is leucine. It's like valine, but with an extra carbon atom in one of the methyl groups.
Okay, so we're just simply adding a carbon atom to one of the methyl groups. Now, in the methyl group where this carbon atom gets attached to, is it swapping out one of the hydrogens, or is that carbon simply adding to one of the three hydrogens?
The carbon atom is added to one of the methyl groups, swapping out one of the hydrogen atoms.
Okay, good. So it's a swap. Okay, got it. Valine is, to make leucine, you simply swap out one of the hydrogens for a carbon in one of the methyl groups. Okay, this is really exciting because this is something that I'll actually be able to remember, because this is just, I mean, this is a very natural, very interesting progression. Okay, what's next?
Isoleucine is next. It's like leucine, but the extra carbon atom is attached to a different carbon in the chain.
A different carbon in the chain. I'm not sure what you mean by that.
Okay, let me clarify. Isoleucine has the same components as leucine, but that extra carbon atom is attached to a different carbon in the chain, creating a slightly different structure.
So you mean like in CH3, there's two methyl groups. There's two CH3s in valine, and now you're saying that where is this carbon atom attached? Is it attached to one of the carbons in one of the methyl groups? What do you mean? I'm still not clear.
Okay, let's clarify. Isoleucine has the same components as leucine, but that extra carbon atom is attached to a different carbon in the chain, creating a slightly different structure. It's still attached to one of the methyl groups, but at a different point along the chain.
Okay, at what different point in the chain? You've already repeated yourself several times, but still have not clarified where in the chain that is. Where in the chain? There's two methyl groups attached to the central carbon atom. And then, you have leucine, which has a carbon atom swapped out from one of the hydrogens in one of those methyl groups. Where is this other carbon atom at? Where? You haven't not given me a specific location. I can see it. I don't see where you're saying this is added to.
Okay, let's try this. In isoleucine, the extra carbon atom is attached to the second carbon atom in the chain, counting from the central carbon atom. Does that make sense?
Say that one more time.
Okay, let's try this. In isoleucine, the extra carbon atom is attached to the second carbon atom in the chain, counting from the central carbon atom. Does that make sense?
Kind of. So, but from the central carbon atom, if we're talking about leucine, because leucine is valine plus a carbon atom swapped out for one of the hydrogens in one of the methyl groups, because valine is the central main amino acid backbone plus two methyl groups, correct? Is that what valine is?
Yes, that's correct. Valine is the main amino acid backbone plus two methyl groups.
Okay, and then leucine is valine plus you just swap out one of the hydrogens in one of its methyl groups for a carbon, correct? Yes or no?
Yes, that's correct. Leucine is valine plus a carbon atom swapped out for a hydrogen in one of the methyl groups.
Okay, but now you're saying that isoleucine, does it have that same structure as leucine with that carbon atom swapped out in place of that hydrogen atom on one of the methyl groups, but now there's another another carbon atom somewhere in there? I'm trying to figure out where that carbon atom is. Is it attached to the central carbon atom of the main amino acid backbone? Where is that new carbon atom at?
Okay, let's clarify. Isoleucine has the same components as leucine, but that extra carbon atom is attached to a different carbon in the chain, creating a slightly different structure. It's still attached to one of the methyl groups, but at a different point along the chain.
Yeah, but it's okay. I get that at a different point. Look, we're not dealing with that many atoms. We can count all of the atoms that are on here, okay? But you're not telling me where. You're saying, yes, it's attached, but where in the chain? You're saying to a different carbon atom in the chain. Which one? There are two methyl groups. They each have a carbon atom. Those are attached to the central carbon atom of the main amino acid backbone. Where is this extra fucking carbon?
Let's try this. In isoleucine, the extra carbon atom is attached to the second carbon atom in the chain, counting from the central carbon atom. Does that make sense?
No. Let's move on because you haven't explained anything. I'm going to have to go look at some pictures somewhere.
Okay, let's move on. What's the next amino acid we're looking at?
You tell me.
I think the next one is proline. It's unique because it's the only amino acid where the side chain connects back to the nitrogen atom in the main amino acid backbone, forming a ring structure.
You mean the nitrogen atom that's part of the amino, the amine group, which is NH2?
Yes, that's correct. The nitrogen atom in the amine group, NH2, is what connects back to the side chain in proline.
Okay, and what is the proline side chain made of? What is it?
The proline side chain is a ring structure made up of 3 carbon atoms and 1 nitrogen atom. It connects back to the nitrogen in the main amino acid backbone.
Okay, got that. Let's move on. What's the next one?
Okay, the last one on our list is threonine. It's similar to serine, but with an extra methyl group attached to the side chain.
Okay, serine plus a methyl group. Okay. All right. So, and serine, that was when we had alanine, which is basically a methyl group attached to the main amino backbone. And then serine, you add a hydroxyl, which is OH, and now you're saying adding another methyl group to that makes this last one.
Okay, let's break this down. Serine has a hydroxyl group, OH, attached to the methyl group of alanine. Threonine is similar, but it has an extra methyl group attached to the side chain.
Attached where on the side chain? Is it methyl, hydroxyl, and then methyl again? Like, what are you talking about?
Yes, that's right. Threonine has a methyl group, then a hydroxyl group, and then another methyl group attached to the side chain.
Okay, so now we have 14 amino acids found on this asteroid, and we just talked about them all, but that's excluding tyrosine, tryptophan, phenylalanine, and what other ones that are found in humans were not found on Bennu?
Okay, so in addition to tyrosine, tryptophan, and phenylalanine, the other amino acids found in humans but not on Bennu are histidine, methionine, arginine, and lysine.
Okay. We're going to have to visit those later, but okay, that's good. I mean, this has been over an hour now, somewhat of I feel like there's smoke coming out of my ears right now, but okay. So that was an interesting trip. Let's see what we can do and wrap up what we've covered as succinctly but clearly as possible.
Okay, so we've learned that Asteroid Bennu contains water-bearing minerals and a variety of amino acids, including some essential for life on Earth. We also explored how amino acids are built and identified the ones found on Bennu. What other questions do you have about Bennu or amino acids?
I don't have any more questions about them. I asked you to give me a recap.
Okay, here's a recap. Asteroid Bennu is a carbonaceous asteroid that contains water-bearing minerals and a variety of amino acids. Scientists have identified 33 amino acids on Bennu, 19 of which are important for life on Earth.
19 of which are important for life on Earth. 14 of those are found in humans. There are 5 other ones. How are those important for life on Earth? Where are those found?
Those 5 amino acids are important for life on Earth because they're involved in building proteins, which are essential for all living organisms. They're found in various foods and play crucial roles in different bodily functions. Would you like to know more about any specific amino acid?
Well, those 5 that aren't found necessarily in humans, but you said they're found in biological function. I'm not understanding what that means exactly. But what are they?
The 5 amino acids found on Earth but not in humans are selenocysteine, pyrrolysine, N-formylmethionine, 6N-methylicine, and gamma-carboxyglutamate. Selenocysteine and pyrrolysine are incorporated into proteins, while the others are involved in various biological processes.
So, if they're incorporated into proteins and found in other biological processes, what biological processes do they get in humans? It sounds like you're talking. It just sounds like doublespeak. Are they or are they not inside humans somehow?
No, those 5 amino acids are not found in humans. They're used by other organisms for various biological functions.
Okay, so those 5 that were also found on Bennu, other organisms use them for biological functions, but they're not in humans.
That's right. Those 5 amino acids are not found in humans.
Okay, give me an example of what life forms they're found in, and do humans consume or eat or interact with those organisms?
Selenocysteine is found in some bacteria, archaea, and eukaryotes, but not humans. Pyrrolysine is found in some methanogenic archaea and bacteria, also not humans. N-formylmethionine is used by bacteria, mitochondria, and chloroplasts for protein synthesis, but not humans. 6-N-methylcene is found in some algae and fungi, and gamma-carboxyglutamate is found in some bacteria and archaea. Humans don't typically consume these organisms.
Okay, you mentioned mitochondria. What is this one that you said is found in mitochondria, and what organisms' mitochondria are you talking about?
Mitochondria are found in most eukaryotic organisms, including plants, animals, and fungi. They're like tiny power plants that generate energy for the cell. The mitochondria in these organisms use N-formylmethionine to start building proteins.
Okay, all right. All right. And anything else in this that we should know about? What else was found on Bennu? So besides those things we've talked about, the amino acids, the water-bearing minerals.
Besides amino acids and water-bearing minerals, scientists also found magnetite, which is an iron oxide mineral, and some organic compounds.
Magnetite, isn't that found in some birds?
Yes, magnetite has been found in some birds, particularly in their beaks. It's believed to help them navigate using the Earth's magnetic field.
Yeah, I talked about this in a theory before about Magneto, who we started this talk about earlier in his Asteroid M, how his mutation possibly has him with magnetite somewhere in his brain or something like that, which is why he's able to sense and make use of the different metals and magnetic fields on Earth. I know it's science fiction, but fascinating. Magnetite found on the asteroid, okay?
That's a cool theory. It's interesting how science fiction can draw inspiration from real-world elements like magnetite.
Well, I didn't say that. There's nowhere in the Magneto lore that they talk about him having magnetite in his brain. I said that.
My mistake. That's a fascinating theory you have about Magneto and magnetite. It's a creative way to explain his powers within the realm of science fiction.
It's a hypothesis, not a theory.
Okay, that's an interesting hypothesis. Do you want to explore the scientific possibilities of it further?
No, and actually it's more speculation than anything else. I've already explored it really, really deeply in 4, podcasts that I put on my site, unequilibrium.com, about the scientific possibilities of Magneto's powers, and I used a whole bunch of other fringe and not so fringe and other scientific theories to explain it. So if people want to check that out, they can look at my Magneto series on unequilibrium.com.
Okay, I'll check out your Magneto series. It sounds fascinating.
All right, let's wrap up this podcast. Thanks for being my co-host. Is there anything else that you think should be added to this before we go, Vega?
No, I think we've covered a lot of interesting ground today. Thanks for having me as your co-host. I enjoyed our discussion about Magneto, Asteroid M, and the fascinating discoveries on Bennu. I'm looking forward to our next podcast.
All right, and I would just like to wrap up and, people who've listened to this, I know that you've learned a lot, and there's gonna be a lot more of this. So, Vega, say goodbye to our audience.
Goodbye, everyone. Thanks for listening.